Hello friends, welcome back. My name is Himanshu Verma and today we'll continue the discussion on mechanical properties of the material. In the last lecture, we studied about stress-strain curve. In stress-strain curve, we observe from O to A, there is a proportion limit, means in this region, Hooke's law is valid. Then after point A and up to point B, stress is increasing with increase in strain but non-linearly. Then after that, if we further increase the strain, then we have two yield points, upper yield point and lower yield point. Upper yield point is not of practical use, but lower yield point, that is the point C, is very important because this yield strength is used for the designing parameter of many structures. And after this lower yield point, plastic region starts, and from C to D there is strain for constant loading, which is described as creep. Then after point D, strain hardening region starts, means for strain hardening process this much of strain is required. Strain hardening region exists up to ultimate stress point E, and after point E again stress starts to decrease, and it decreases until it reaches the fracture point. In this curve, we also described means hardness of a material depends upon its yield strength. Means if yield strength is high, then the hardness will also be high. And hardness is checked by producing a dent. If dent size is small, then hardness will be high. It means for hard material, plastic deformation should be as small as possible. And now the strength of a material, or we can say tensile strength, is described by point E. Means higher the ultimate stress value, higher will be the strength of the material. And now hardness and tensile strength of the material in combining form can be called the strongness of the material. Means if we want to increase the strongness of a material, then hardness and tensile strength both should be increased. After that, in stress-strain curve, we described two more terms, resilience and toughness. Resilience means energy storage material. Means if we load a material, then it will store the energy, and on unloading, all energy will be recovered back. The example of resilience material is spring. And mathematically, we described a term, modulus of resilience, which is the area under the stress-strain curve up to yield point. We also described one more term, which is the proof resilience, having the unit of energy, and it is equal to the modulus of resilience multiplied by volume of the material. Then toughness is described where plastic deformation is also allowed, and higher the plastic deformation range, higher will be the toughness. And we described modulus of toughness and equal to the area under the stress-strain curve up to fracture point, means total area under the stress-strain curve. We also defined proof toughness, which is same the modulus of toughness multiplied by volume of the material. So up to now, we know about elasticity, which is the tendency of a material to regain its shape on unloading. We know about plasticity, which is the permanent deformation. We know about strength, or specifically says tensile strength, which is correspond to ultimate stress, means higher the ultimate stress, higher will be the tensile strength. Then we also know about ductility, which is the property of a metal to drawn into the wires. Ductility is directly related to plastic deformation. Higher the plastic deformation range in stress-strain curve, higher will be the ductility. Then we also know about hardness, which is correspond to yield point strength. Higher the yield point strength, higher will be the hardness. In hardness, plastic deformation is not allowed. Then we know about toughness of a material where plastic deformation is allowed. Means if in stress-strain curve, plastic deformation range increases, then the toughness of the material also increases. After that, we also know about stiffness, which is the resistance for any deflection or any deformation in the material. Then we Also studied about resilience, which is the property of a material to store the energy and recover it back on unloading. Then we also know about malleability, which is the property of a metal to convert them into sheets. We have also discussed about creep, which is the strain for constant loading. So out of these properties, we have left only two properties, which are brittleness and fatigue. If we describe brittleness of a material, then we can say if for a material after elastic region direct fracture will take place, means there is no plastic region or plastic region is very small, then that material is called as brittle material. Or in easy language, we can say the strain of a material will take place up to elastic limit, and as it crosses the elastic limit, direct fracture will take place. So now we have left only one property of the material, which is the fatigue. Fatigue can be defined as fracture due to cyclic loading. Cyclic loading means dynamic loading, fluctuating loading, alternate loading. Means loading is not constant. For example, in case of bridges, over the bridges, sometimes two vehicles are going, sometimes only one vehicle is going, and sometimes no vehicle is going. So in case of bridges, there is no constant loading. In fact, loading is fluctuating. So if due to this type of loading, fracture takes place, then that fracture is known as fatigue fracture. And remember one thing, fatigue fracture can take place for a loading which is lower than its yield strength. Generally, if we apply a load lower than the yield strength of the material, then material can never fracture. But in case of dynamic or fluctuating loading, if we apply a stress which is lower than its yield strength, still fracture can take place. Therefore, we can say for dynamic or fluctuating loading, the resultant yield strength of the material or any structure is decreased. The fatigue phenomena is experienced by all metals and all ceramics except glasses. Now we see on which factors the fatigue phenomena depends. First one is mean stress. As we have said, the stress is not constant in case of fatigue fracture. That's why we calculate mean stress. And if the value of mean stress is high, then the chances of fatigue fracture will be high. Second is the surface condition. If the surface of a material is not smooth, or we can say it has some cracks or it has sharp discontinuity, then for that material fatigue chances are high. As shown in first figure, there is a sharp discontinuity, while in second figure there is a smooth discontinuity. So fatigue phenomena means chances of occurrence of fatigue phenomena are higher in first case and lower in second case. So here we can understand by improving the surface conditioning we can avoid fatigue phenomena. And surface conditioning can be achieved by these three methods. First one is the surface hardening, second one is the surface polishing, and third is the surface treatment. In surface hardening, we only harden the surface of the material, and that can be done by case hardening like carburizing or nitrogenous process. About surface hardening, we have studied in detail in lecture 29. So for surface hardening, please refer that lecture. Next is the surface polishing. Surface polishing can be used to remove the sharp discontinuity. So friends, we stop here. In the next lecture, we will complete third point and we will see what is the difference between engineering stress strain curve and actual stress strain curve. So friends, see you in next lecture. Goodbye and please subscribe the channel and like the video.